In this section, we'll be discussing the basics of chemical bonding. We'll be looking at ionic bonding and molecular bonding. And ultimately, the idea here is that this bonding involves the interactions between electrons from one element to the nucleus or the protons of another element, and how those things are interacting, or how those are even being shared between the two atoms. We have to also look at electron configurations of ions, so when they lose electrons or gain electrons, and also we're going to do some accounting of those, the difference between the number of protons and the number of electrons, and determine the formal charges of different elements within a molecule. We're going to talk about Lewis symbols and how to create them and look at them, what happens with the ions for those, and Lewis symbols for molecules. We'll be talking about covalent bonds as well in terms of molecular bonds, the octet rule, multiple bonds, and how that looks in terms of electrons. We will discuss some of the energetics of bond formation, electronegativity and polarity. That is an important feature of bonding. And we'll talk about resonance structure and then classify organic compounds. So this whole section. We'll only cover a little bit of this in this current lecture. The chemical bonds are basically the attractive forces that hold atoms together, and the reason they're held together is because of that positive charge in the nucleus from the protons and the negative charge of the electrons in the outer shells of the element, and how those things are interacting with each other. So why do we want to study this? We study this because it's really the basis for all of the chemical reactions that are occurring. It allows us to make predictions on what kind of things might happen and why they might happen. We need to understand how we break bonds and how the new bonds are going to form and why those things are happening. First kind of idea I want you to think about, breaking bonds always requires energy. If you think about this as someone holding your hand, in order to break that handhold, you have to use energy to pull those hands apart. But when you put those back together, then that will actually release energy. So bond breaking requires energy. The formation of new bonds actually generally will release energy. Now, covalent bonds, you can kind of see in this figure where we have these different shells of electrons. The valence shells electrons are actually interacting with both of these different nuclei, so they're kind of overlapping. So we'll have this covalent bonds occurs in molecules, and it involves the sharing of electrons between different nuclear centers. However, ionic bonding is going to occur in ionic solids like salts, and the electrons will actually be transferred from one element to another. For example, sodium is going to lose an electron to chlorine, and that's a transfer. So it is more associated with this chlorine element, the electron is, than the sodium. But because now there is an overall charge of the chlorine as a negative charge and the sodium is a positive charge, they will have still this kind of interaction or attractive force, but the chlorine is no longer sharing the electron with the orbital within sodium. So it's another way to look at it. It's a little more simple in terms of how these things are happening, and we'll look at this ionic bonding first. Ionic bonds result from attractive forces between oppositely charged particles. These are generally going to be between metals, like sodium, and nonmetals, like chlorine. So if you remember the periodic table, there's this line kind of diagonally from boron. Things on the upper right side are going to be nonmetals. Everything else is a metal. And those are when we are going to generate ionic bonds. Metals have low ionic energies or ionization energies, which means that it doesn't take a lot of energy to pull off an electron. So they're easy to lose electrons. Nonmetals have an exothermic electron affinity. So the affinity part is for them to pull electrons toward themselves. And we can kind of get an idea by looking at the electron configuration between sodium and chlorine. So if you look at sodium electron configuration, you'll notice that we have 2 electrons in the first shell, and we go into the 2s and 2p, so we have these electrons in the second shell. We go into a bigger shell, the 3s shell, and there's 1 electron out there. So sodium, this really far away electron, is easy to pull off. That's why it has a low ionization energy. Chlorine, for example, we're in the 1s, 2s, and 2p. We get into the 3s shell, and there are a lot of electrons in here already, which means there are a lot of protons that are attracting all of these electrons. And we have these things, we have this 1 electron out here, and it doesn't take a lot of energy for this electron, for example, to hop in here. All of these other electrons are already in this outer shell, so it's just 1 extra electron in there. It's actually a very exothermic electron affinity. Chlorine really likes to fill that spot up with another electron. So the other thing that we'll talk about is the formation of lattice energies. The lattices stabilize this, and I'll talk to you about that in just a moment. So here's the first kind of step here, the ionic compound, just as I showed you before in that last slide, where that sodium, 1 of those electrons will remove here. So this electron from the 3s orbital will bump down and leave this element and can be attractive to the chlorine element. So then we'll have a positively charged sodium, negatively charged chloride ion, and this is then an ionic bond between this positive and negative ions of this compound. Why does this occur? Why is the electron transferred? Why sodium plus and not Na2 plus or Na negative, chlorine negative, or -2 or a plus? Again, this all goes back to this electron configuration, and if we had to add another electron, it would have to go into a higher energy electron orbital, and it's just not going to be a very stable element. Chlorine, for example, doesn't want to necessarily lose this electron because there's a lot of positive charge, right? Remember we talked about that net effective charge that these electrons are seeing, and it's seeing a really positive charge coming through these initial 2 shells. So there's still a really positive charge. So pulling one of these off is going to be relatively expensive in terms of energy. This is also one of the other parts of this idea, is this lattice structure. We get this lattice, we know that this exists in a 3-dimensional structure, and these elements are going to have some amount of interaction with each other, and they're going to form these kind of ionic bonds between them that help to recover some of that energy of transferring those electrons over. So when we write ionic chemical formulas, we always are written as empirical formulas, where the smallest whole number ratios of the cation and anion. So 2 different pathways to evaluate this energy. First, we're looking at the sodium and releasing an electron, so the ionization energy of sodium. That's actually going to cost us 495.4 kilojoules per mole of energy. So we have to put in that amount of energy to rip off that electron from the sodium element. However, when we are going to add an electron to chlorine and we make a chloride ion, that actually releases energy, 348.8 kilojoules per mole. So is this energetically favorable? Well, right now, with just the ionization energy and the electron affinity energy, we'd actually say this was not favorable. It actually we would have to still input some amount of energy, 150 kilojoules per mole overall, than what we'd get out. So this wouldn't be actually energetically favorable at this point. But what we have to do is we actually have to add the lattice energy. So there's a certain amount of energy when we have a sodium ion and a chloride ion in close proximity to each other. They will make this ionic bond with each other, and that will actually release extra energy in that system if they're able to interact with each other. And here, then, we will have an overall difference of negative 411 kilojoules per mole. So now this is actually very energetically favorable, and it releases a lot of energy into the environment. And here's an idea of what's going on and how this lattice energy works and where this energy comes from, right? So on the left side, we have gaseous sodium chloride. On the right, we have a solid crystal sodium chloride. So where does this energy come from? Remember, we're talking about when these are in a gas stage, they have a lot of kinetic energy. They have rotation, translational, vibrational energies. But when we move over here in this lattice, we've lost all of that energy, and the potential energy of the system is decreased when the solid salt is formed from the gas phase. So this actually is that decrease in energy is going to be a release of the energy from the system into the environment when that lattice energy is formed. So now we have a little bit more information regarding why metals form cations and non-metals form anions. And it really comes down to this Aufbau principle and electron configuration. So let's look at, first of all, one of the big things is that this n value, the principal quantum number that describes that shell, that size of the shell for the electrons, is going to be really important. So let's look at an example of chlorine. And here we have the electron configuration written out. And we have these, we can also simplify this as the noble gas configuration. We have one spot. Remember, p orbitals can have 6 electrons because p, we have that pin shape. It has 3 orientations in the x, y, and z axes. So we could have up to 3p6. If we add 1 electron, we get the noble gas configuration. Right here we go from 5 to 6 of argon. It doesn't take that much more energy to add an electron. So that's typically why chloride will become a negatively charged element. And it doesn't take that much energy to do that. However, if we're looking at sodium, we wouldn't necessarily want to add another electron, especially when we're thinking about that effective charge of that element. So again, we have this 1s orbital with 2 electrons in it for here. And then we're going to add another bigger shell on the outside of that, where we're going to add that 2s electrons. And we're also going to get the 6 electrons in the p orbitals here. Then at the very end, we're also going to now create one more bigger orbital on the outside, which has this 3s, this 1 electron out here. Now the effective charge in a sodium element, if we have 11 protons in that nucleus here, we know that we have 10 electrons in the core, and that is going to be, right, the 6, 7, 8, 9, 10 in the core. So the effective charge that this element's seeing is 1 plus 1 charge. But that's not very strong. It's just a plus 1 charge. It's not like we have a plus 2 or plus 3 or plus 5. So there isn't very much strength in that charge. It's kind of like a really weak magnet. So we're able to pretty easily remove that electron. And then you can see here, once that electron's eliminated, that noble gas configuration looks just like neon. So we are then left with those core electrons as the size of the element. So if we start digging too much into this layer, into the core, now we can see that effective charge is going to be a lot higher for these electrons. Remember, because the elements in the same principal quantum number shell, those are going to be feeling that same effective, that charge. So if we have 11 protons are still in here, and we are only being shielded from the inside by these 2 electrons here, we would actually have effective charge of a plus 9, and that is going to be a lot harder than to pull electrons out of that those core shells. So this is kind of the end of how many electrons we really pull off, but this is stable still because removing that 1 electron wasn't that hard. Removing additional ones are going to be much harder. So I just wanted to look at the energetics of that in terms of kilojoules. That first ionization energy, the first electron pulling this first one off, is only 500 kilojoules per mole. It's pretty small, not too hard. But if we want to start digging into this 2p6 orbital, for example, then it's almost 10 times more difficult, 10 times more energy is required to pull that electron off. So the first electron can move pretty easily. The second one, that's not going to happen. Here's an example of an element from the second column, calcium. This is the electron configuration of calcium with the argon in brackets, and then we're in the fourth shell. It's an S2 is the 2 electrons in that shell, and ionization energies are not high, where it's about 590 and then about 1000. So it's still getting higher as we pull off that second one, but it's still manageable. And if we now go into these core shells in the 3p6 orbital, for example, in argon, that would be in here, now this energy gets quite a lot higher. So it's about 5-fold more energy required. We can regain about 2000 kilojoules from the lattice energy if we're at a +2 element. That recovers this initial ionization energy, but it's not going to be able to be recovered with this ionization in the third one. So the third electron is too hard to remove. We're not going to recoup that energy through the lattice energy. So calcium, a +3 calcium doesn't form. So some generalizations for this electron configuration for ions. When ions form, the S and P block ions tend to gain or lose electrons to obtain the nearest noble gas electron configuration. So they're trying to get to that noble gas configuration. That's generally going to give you the best idea of where the ionization energies are going to be most favorable, or electron affinity energies are going to be most favorable. The octet rule is this idea where we tend to gain or lose electrons until they've achieved an outer valence shell containing an octet of 8 electrons. Again, that is going to be from the s orbitals, which allow you to have 2, and the p orbitals, which allow you to have 6, and those are going to be 8 electrons. And remember that when we're talking about putting these are the only ones on the outside. The d and f orbitals, those are going to be core electrons, and those are not going to be part of the valence shell. So this is why the octet rule works, and this is maybe if you've done this in biology courses, we're always talking about 8, even though you think about those higher energy electrons, the D and F orbitals are higher energy orbitals, but they're shoved back into the core, so those are not accessible for chemical reactions. The octet rule works really well for metals in the first and second columns. It doesn't work as well in the transition metals because of some of the more complex things that might happen where electrons might hop around into different orbitals to create some stabilities. Also, obviously, hydrogen and helium can't obey that because they're in the upper shell here. They are only in the 1s shell, and you can only hold 2 electrons in there. So those are going to obviously create an issue. You're not going to have 8 electrons in an s orbital. So it doesn't work with the transition and post-transition metals. Before we get into the next section regarding Lewis dot structures, I would like you to take a look at this question and write out the correct electron configuration for cesium and the charged version of cesium. Now that we have a little bit of experience with electron configuration and what those things mean and where electrons are found, now I want to introduce you to this new idea called Lewis symbols, or the Lewis structures. And this is really a bookkeeping method, an accounting method for the valence shell electrons. So the electrons in the largest principal quantum number shell. We write the chemical symbol and then we surround that with the number of dots next to the symbol associated with the different electrons. So for example, if we're looking at hydrogen, lithium, sodium in that first column of the periodic table, each of these has 1 electron in that valence shell, in that s shell. So it's NS1, that would be the number of electrons. For the next column, we have helium, beryllium, magnesium, calcium, for example. These would have 2 electrons in their valence shells. We can move over on the periodic table. These are the tall rows. For reference, they don't include the transition elements. We don't use Lewis symbol for the transition elements because of what we were just talking about before, where those tend to like to be half or completely filled. It gets more complicated than this. Lewis symbols are really good for organic compounds and generally biological compounds that utilize some of these elements on with the longer, taller rows that don't include the transition metals. So that first row in the 3A, the boron, we have 3 electrons in that valence shell. We have the 2 from the s orbital and then 1 from p. Aluminum is also that same way. If we go into the next column, we have calcium and silicon. Those are going to have the 2s, 2p organization. So each of these has 4 electrons in their valence shell. Now we're going to go into the 5A next. And we can see we have nitrogen and phosphorus. They'll have the 2 in the s orbital and then 3 in the p orbital. So they'll have complete 5. And then we go to the 6A with oxygen and sulfur. They'll have 6 valence shell electrons. And then fluorine, chlorine. And then finally the noble gases. And we brought helium over here as well. Obviously those don't have p orbitals. They're in the top row. They only have the s orbitals available to them. So this is a way that we can look at the electrons and how many might want to come in. For example, all of these 5A, 6A, 7A, we have spots available for electrons. And we typically do this on 4 different sides. So we have 1, 2, 3, 4, 5, 6, 7, 8. So those 4 sides, those represent different spots where electrons can go into. So here we can also look at using this to start to kind of examine and look at chemical reactions. In organic chemistry, when we have arrows here, these arrows actually mean specific things. So we always draw arrows from electrons to where they are going to go. This seems to be confusing for a lot of people doing this, but this is the standard use for the arrows within chemistry, looking at electrons being at the base, and then the arrow points at where they are going to go. Notice this is 1 electron, and it's actually a one-sided arrow. It just means that it's just moving 1 electron. If you have 2 arrows, or a 2-sided arrow, you're moving actually 2 electrons. So we can use the dot structure to show this transfer from sodium to chlorine, or now a chloride ion. So the sodium is going to be a positive charge because it lost that electron. And you can see here that blank spot now has that electron and it becomes negatively charged. We can do this with other elements. We have magnesium is losing 2 electrons, oxygen gaining 2. So this Lewis structure helps us to organize and account for electrons. We can't gain or lose electrons from an equation. So it's just like balancing it's just like balancing an element in the periodic table. You can't have just the creation of a water from nowhere. It has to come from somewhere. The same with electrons. Those are matter, and you can't just create those out of thin air. They have to come from somewhere. So this is just our accounting system to make sure that we know where the things are. And notice the charge here, a +2, a -2. The overall charge on this side of the arrow is a 0. The overall charge on this side of the arrow is also a 0. So we have a 0 charge, and then a plus and a minus. That's also a 0 charge. So charges, remember, those have to be balanced, and really it's talking about balancing electrons. This Lewis dot structure idea starts to introduce us to this idea now of covalent compounds, because the Lewis structure is showing us, remember, the valence electrons, and those are the electrons that are outside, the furthest away from the nucleus, the most available and able to interact with the surrounding, the outside environment. These are the spaces where atoms start to be shared, and they can be involved in being shared by other atoms. And this is called, when that sharing happens, called a covalent bond. So let's look at this process in action here using this Lewis dot structure idea. If we have hydrogen gas, we have a hydrogen with one electron, hydrogen with another electron. Remember, hydrogens have one proton. They would have one electron. This is the most simple covalent bond where we have, but in an s orbital, we have room for two electrons. So they have space in their orbitals. They each have space. And now we have two electrons here. We have two protons. So they have fused together. They have created a new bond that would release energy from this starting point. Right, so we have a lower potential energy. They've come together, and now we can also write this out as these sharing electrons here. We can write it out as a single line. So that is the same kind of idea. If we have a line, it means there are two electrons being shared between that bond. Another example is fluorine. So if we have a fluorine compound, 1, 2, 3, 4, 5, 6, 7, like I showed you in that last chart, looking at the various elements, fluorine is going to have, and all of the elements in that column are going to have 7 valence shell electrons. They can use this open spot here in each of their orbitals to allow for bonding. And this is equivalent to, right, these two electrons are being shared. This line means that those two electrons are being shared. And this is going to form a single covalent bond. These electrons now on the outside, these are called lone pairs of electrons. So we have 1 lone pair, 2 lone pairs, 3 lone pairs per fluorine compound here. So 3 on each. And those we're going to want to keep track of because we're going to have some interesting things that we use with those later on in the semester. This is the same exact structure that you're going to see for chlorine, bromine, iodine. If you're just basically replacing the F here with the Cl, Br, or I. But because they're in the same column on the periodic table, they're going to have that same Lewis structure for the diatomic gases. We can also have diatomic gases which are multiple or different types of compounds. So hydrogen and fluorine, for example, we have 1 electron hydrogen, we have 7 in fluorine. They both have a spot here for bonding, and we can put these together, and this line again represents those 2 shared electrons. HCl, HBr, HI, this is the same concept and the same things that are going to happen. Next, I want you to think about how many electrons are required to complete the octet around nitrogen. So the hint here is to determine the valence electrons. What's the starting point? How many do they have? And how many more do we need to get to that octet? Remember, octet is 8, and that is filling up the s orbital, which would be 2, and the p orbital, which can hold 6. So 6 plus 2 is 8. That's where that octet rule comes into play. Determine this, post your answer in our Blackboard space, and then I'll move to the next step. So we just went over a few simple Lewis structures for very simple compounds. I want to show you still fairly simple, but kind of moving up in complexity here. Methane gas. This is an element that contains carbon, which has 4 valence electrons. And as you have maybe guessed, if we want to get to 8, we need to add 4 more electrons somehow. So one of the ways to do that is by loading that up with hydrogen elements, which each are going to provide 1 electron each. So these are 2 different ways. Here's the Lewis structure, dot structure. This would be a traditional method for showing you these single bonds that are sharing 2 electrons in each bond here. This is methane gas. This is the structural formula for methane gas. Nitrogen, you'll notice it has a lone pair of electrons. So these are paired up already, but they have spots for 3 more electrons. So we can do the same thing. We can load it up with hydrogens, and you've guessed it, we need 1, 2, 3 hydrogens here. And these are going to show you those shared electrons with those lines, and then the lone pair on top. We're going to now look at oxygen. These have 2 lone pairs, 2 open spots here, and we're going to add 2 hydrogens. This is the formula for water. You'll see it's sharing 2 pairs of electrons, the oxygen and the hydrogen, and the oxygen and the hydrogen. And the oxygen also has 2 lone pairs of electrons. This is really important for the shape of this compound, and we'll talk about shape in the next chapter. Those previous examples were showing you single bonds, like the methane gas. We have one pair of electrons being shared. We can get more complicated where we actually share more than one pair of electrons. And that is going to be kind of demonstrated here. If we have oxygen with these 6 valence electrons and carbon with 4, the starting point, we can actually share these 2 oxygen electrons with these 2 spots in carbon and these 2 unshared, unpaired electrons with carbon. So we're going to donate all of these, and we're left with something that looks like a Lewis structure of this, where we actually have 1, 2, 3, 4 being shared between this oxygen on the left and the carbon, and then 4 more with the carbon in the center and the oxygen on the right. This is equivalent. Now we draw these 2 lines. One line is equal to 2 electrons, so 2 lines is equivalent to 4 electrons. 4 electrons are being shared on the left side, 4 electrons being shared on the right side. This is carbon dioxide. This is how this looks, and this is the Lewis dot structure for carbon dioxide. Finally, we do have triple bonds as well. This is the last type, and we'll talk about this later when we talk more about the symmetry and the orientation, the geometry of these things. But we can share 3 sets of electrons or 3 pairs of electrons, and this will give us a triple bond, which we have 2, 4, 6, right? Each one of these represents 2 electrons being shared, and so this would represent 2, 4, 6 electrons being shared, also shown in the middle here in the same way. But this is typically how nitrogen gas is going to be shown as in a Lewis structure. All right, so now I want you to look below, and here I want you to look at what species is most likely to have multiple bonds. In order to do this, you're going to want to just kind of how to figure this out. First of all, you want to look at the number of valence electrons that these compounds are going to have. Usually you want to look at that thing that's going to have the least number of valence electrons and likely to have to add the most number of electrons to give it an octet. Everything you're going to want to have an octet. Never use hydrogen as that molecule, though. Hydrogen's always kind of the filler. It fills in those gaps where electrons are needed. So, for example, look at the difference between carbon and oxygen. How are you going to connect these and give them both an octet? Oxygen, we kind of looked at water before, so likely probably not that one. This phosphate, the boron, the carbon. You want to focus on these elements here, and how do these other elements fit around to provide that, to determine if one or the other is going to have multiple bonds. Post your answer in Blackboard and we'll discuss this. Now that you've been introduced to Lewis dot structures and covalent bonds, I want to look a little more closely at what's happening with the electrons in those covalent bonds. And this is a diagram below looking at kind of a scatter plot, the probability kind of going back to those probabilities of a sphere, the s orbital, where the electrons are going to be found. And when these come together and bind, they're actually still, these electrons are going to be found anywhere in here. So they have the single orbital. They're going to have probability of being in here in any spot at any one time. And the distance between the nuclei, you can see these dark black orbs here are representing the protons. Those come together and they're going to be a lot closer in distance than they were as individual atoms. So these nuclei pull closer together and they kind of pull these and tether these nuclei together in this form. In a covalent bond, there are really 2 different things that we're looking at to determine the energies involved and the strength of those. So we're looking at the bond length, and that's the difference, the distance between the 2 nuclei of the 2 different proton groups. And this is going to tell us something about that bond character here. The other thing we look at is bond energy. Remember, when a bond forms and these 2 protons, for example, come together, there is going to be energy released because this releases energy as these electrons come closer to more positive charge. If we want to break this bond and pull the electrons away from those other protons, then that's going to require energy. Bond length is one characteristic, and the amount of energy that's associated with that bond is another. There's an interesting characteristic with that bond length and energy as well, because as we start to push those protons together, they start to repel each other. So there's only a certain distance that we can get those, and as we start to push those closer and closer, so here's a graph of the distance of separation, so really far apart would be on the right, really close together would be on the left side of the x-axis. And when we're going from low energy on the bottom here up to high energy, this state with this red line, this is telling us this is the lowest energy state when they're 75 picometers apart, for example. If we start to rip them apart, then this requires some amount of energy to pull those electrons away from the other proton. But if we start to push them together too close, then the energy starts to increase because the protons start to repel each other in the two different nuclei. So you can only get them so close. And then this energy rises a lot because we'd have to push them. There we require a lot of energy to fuse these together, to push those protons together into one group that would then essentially create a new element. If we, for example, push two protons together, then that would be helium, for example, instead of hydrogen. Here I want you to look at this question determining what is the primary driving force behind the formation of covalent bonds. One of these answers is correct. I want you to indicate which answer you feel is correct and why, or why the other ones are not correct in your answer that you post in Blackboard. Here's a kind of similar type of question. What forces limit the distance between the nuclei in a covalent bond? And here are 5 different options. I'd like you to tell me which one is the correct one and why it's correct by either describing why the answer you gave is correct or why the other 4 are incorrect. In the next section, we're going to start talking about electronegativity in these types of bonds and bond polarity, essentially where we're looking at two different nuclei. So here, if we have the same nucleus with it's a single proton in each one, those electrons are going to be found here in this space pretty much evenly around one versus the other. But when we have different shielding, or we have different amounts of protons in one side versus the other, like when we're sharing electrons with hydrogen versus chlorine, there's going to be a difference in where we find the majority of electrons. And where these electrons, even if it was from originally the hydrogen, where that electron is found, it's going to be a higher probability it's going to be over here by the chlorine than it's going to be over here by the hydrogen. And we're going to talk about that in the next section.